We're talking about quantum computing. Preeminent expert in the field is here. So very.
Yeah, my quantum sense was tingling, so I had to jump in.
Yes.
I just felt a disturbance and I had to log on.
Yeah, exactly.
What's up? What do you guys, where are you in the explanation of why the recent announcement is like overhyped?
Yeah, so I mean, if I'm shining a photon on this, you're shining a searchlight on it. So I don't have the requisite skill, but basically the way I looked at it was circuit sampling is not useful, and Google still keeps trotting out circuit sampling. Maybe you want to start with that, and like why to anybody?
Yeah.
Why does that? What does that mean? And am I right?
I was in the room last time it happened, right? 2018, 2019. Really, it's just creating randomness. It's like running a hash function, right? It's just a very complex function between the parameters of the circuit, like how you're doing these quantum bit rotations, and the output wave function that you sample and its distribution, and predicting, predicting in which order the bit strings come in terms of like their heaviest weight. So that means like, what are the most likely outcomes, and ranking them is really, really hard for a classical computer, right? That's cool, but I mean, it's basically RNG, right? It's like a weird RNG algorithm that's quantum. But what that shows is the quantum computer can access quantum states of high quantum complexity. And quantum complexity is not the same as classical computer complexity. And there's a separation between the two, such that, if you're trying to emulate a quantum computer to get, prediction of this distribution, it's going to cost you a lot of compute, right? And so you get these very dramatic sounding numbers, right? But the reality is like, can you use this for something other than, hashing? Not really, right? Initially, back in my days, we were looking at these circuits, these parameterized quantum circuits, to train them like neural networks, right? To train the parameters of gradient descent. And there was many years of research, and the core paper came from Google. There was this paper, Barron plateaus and quantum neural networks landscapes, at least quantum neural networks shaped like the one they just ran, which are called random parameterized quantum circuits. And the gradients can't train them, and doesn't matter how you cut it. So that's like the TLDR of several years of research there. Of course, there's like, there are circuits that you could run on a better computer that you can train. And then the question is like, can those circuits do something interesting? And the answer is probably, but we can't test that right now because the quantum computers aren't big enough. And, deep learning is an empirical science. It's kind of hard to make theoretical guarantees about deep learning performance. You kind of have to compute, empirically. And so, the field kind of got stuck there. We try to make these circuits useful. We couldn't. And to the best of my knowledge, the field is still stuck there. I still see papers from this year on like how these are untrainable.
Yeah.
So that era of quantum computing is dead, like what is called the NISQ era, noisy intermediate scale era, like to make this sort of power useful. It's just not, right? The fidelity is too low. It's 0.1% fidelity of the output state. It's not useful for your, quantum chemistry calculations, whatever you want. It's too, the states of high complexity are too low fidelity, right? Of course, you could create states that are lower complexity. You do less operations enough because, there's an error rate per operation. And that's the simulation demos they've done. But those are pretty basic, and usually they don't have an advantage over classical computers. So there's been no demo of a useful thing that can't be simulated. There's demos of useful things that can be simulated on a classical computer. And there's been demos of useless things that can't be simulated on a classical computer. But a full quantum advantage would be both simultaneously, for one thing. Now, the way to actually get to that zone is you need much better quantum computers. And to have much better quantum computers, you got to constantly detect errors in your quantum computation and undo the errors, right? And filter them out. And that process is called quantum error correction. So that was the other part of the demo. They actually had 2 chips in the announcement. And the second chip was doing quantum error correction with 49 qubits, up to 49 qubits. And, I think pessimists used to say quantum computing is never going to work because they don't think you can even do quantum error correction. Those skeptics had no theoretical basis to ground themselves on. There was a very rich theory of why this would work. And you just needed to get the engineering dialed in, right? The quality of each component. The big difference between 2019 and now is that they found a way to factor out qubits and factor out connections to qubits that are faulty in the manufacturing, because yields are it's very difficult to have a big grid of bits that are essentially perfect, because any defect in the material, any like doping that shouldn't be there. And so that allowed them to scale up a bit here and demo what is called the surface code, which Kitev came up with, some scientists from Caltech who now works at Google. And that's very exciting. I think that's very exciting that the surface code was demonstrated. It's like the most theoretically well understood quantum error correcting code. It's just like, it's kind of like break even. It's kind of a demo of like the Q factor for nuclear fusion, but on a very small scale, right? It's like you have a tiny reaction that's break even, and like in theory, if you scaled that, it would overwhelm like the overhead of like keeping that going. But there's never been an end-to-end positive sort of energetic ROI nuclear fusion demo.
Right.
Similarly here, there's no end-to-end positive ROI demo of quantum computing, right? In terms of like all the compute needed to support it and energy compared to what like the benefits you get. So that's how I would summarize it. Yeah.
Yeah, and so that like one of the questions that I think for Wall Street is basically, so we made a step forward here, or Google made a step forward here. Does that mean quantum's around the corner? I think obviously anybody even remotely skilled in the art knows the answer is no. But one of the things, as I dusted off some old papers and things like that, is that I was curious about was the whole idea of the physical to logical kind of ratio, and that we're still at subscale to the point where we don't even have kind of a number we could throw out. It was often hypothesized that you would need 1,000 physical qubits to get one logical qubit, and at least with encryption, it would seem like if you had a 2048-bit RSA key, you would need around 4,000 qubits or so, 2x, to decrypt it. So if you can go from there, you could say, okay, well, if I need 4,000 logical qubits, maybe I need 4 million physical qubits. And I don't think this announcement changed anything on that front, but I was curious if my assessments are correct, or if you have a lot to add or explain there.
Well, let me qualify that. Yeah. So what you just described, the physical to logical ratio, depending on the code you choose, right? The encoding of quantum information on the quantum computer, the architecture of your quantum computer, you'll get different ratios. And, with a bigger ratio, if you use way more physical qubits and your code is good and everything's good, then you have way more robustness to noise, right? So maybe you have a longer lifetime. But you're right. Like right now, they demonstrated 49-to-1. They also did 25-to-1. And basically that was the scaling they demonstrated. As you scale it up, you get better coherence in logical space. In principle, they're probably going to want to scale it up to 1,000-to-1. I think that's their next stage in the roadmap, like a full logical qubit. And then they're going to put two of those together. And then in principle, they want to scale to, 10 million plus qubits. But you're right, it's going to take several million. You got to do a lot of accounting, but it's giving the millions between 1 and 10 to do Shor's algorithm. And the thing is, right now they're a single chip, right? And it's not that small, right? Like there's pictures of like the chip and people holding it in their hand. And if you look at a photo of the fridge and all the connectors, like it's pretty packed. So IBM has technology where they have bigger fridges, and they can get a bit bigger, but at some point they're going to have to go multi-fridge, and there's going to be massive errors from the interconnect, because the interconnect has to be quantum. It's basically got to be a mini quantum LAN, right? Local area network.
Well, this is what I was curious about, because I spent a lot of time reading about whether it's surface plasmons or superconducting qubits or ion trap. And I think the challenge in engineering, and you've actually done this stuff, but as somebody who's read about it, going from 100 of anything, whether it's transistors or molecules, things that I've worked with, to from 100 to a million is very
Yeah.
challenging. And
Yeah.
you mentioned dilution refrigerators. So to me, is there one of these approaches that's more given to scale?
Mm.
I can imagine the ion trap lasers, kind of that would be
Mhm.
get kind of crowded and like difficult to maneuver those.
Yeah, but they
Uh,
could scale initially faster to like 1,000 or maybe
yeah,
10,000 in a single trap, right? And that's what you're seeing with Q-era, with IonQ, with Pascal with a Q, Atom computing. I think they're at 500 because those are different computers. They make atoms float in 3D by pulsing them with lasers to cool them and like basically hold them there, right? But they could arrange them in 3D, right? So you could kind of densely pack in a certain volume a certain number of qubits, but then you're bottlenecked by how many lasers can you multiplex into one trap, right? And that's very difficult. Of course, they're trying to like shuttle ions between chips, TBD what the fidelities they're going to get there. But to be fair, like there's been some demonstrations of interconnect for ion traps. There's been demonstrations of interconnect for superconducting, but putting it all together and getting good numbers end to end is going to be very difficult. It took 5 years to go from 50 qubits to 100 here
right,
for this demo.
right.
So, I hadn't checked in on the team in a while. I left a while back because in 2019, I started a different team working for Big Boss on quantum internet and sensing because I thought it had more potential than near term. And look, I think they've made they're trying to battle Mother Nature, right? Like the Google team's arguably the best team on earth right now in quantum computing, and they're very skilled, very smart people. But like this is a really hard problem. A lot of people like literally gave up, quit. It's just a really hard problem. It's kind of like nuclear fusion. You kind of get blackpilled over time. But look, they demonstrated quantum error correction was possible, which honestly is very impressive. Does that make me bullish? I don't know. I think there's other challenges around the corner. But I think this was like the minimum viable result to keep the effort going, right? To me,
Yeah.
probably a few years later than they wanted. I think if you scrape YouTube, you'll find like roadmaps where like stage 6 was supposed to be 2030, the million qubit, right? And now there's no years on it, right? So,
Right.
but
Right.
at the end of the day, they pumped the stock 5%, so they paid for themselves, 10 times over,
Oh
right?
yeah. I mean,
Uh,
I think a lot of people are focused on Rigetti and IonQ because they're public,
yeah,
um, through
yeah,
the
it's more
SPAC process.
concentrated, pure play. I was the first user of Getty. I have some affinity to them. They were early. Uh, I don't know. They don't seem like at the end of the day, like your computer gets like almost doubly exponentially. You know what double exponential means? It's exponential in your exponential. Your computer gets almost doubly exponentially more valuable with the higher fidelity each single and 2-qubit gate is, right? So if you were to price the computational power of quantum computers according to like their compute volume, like Google and IBM would be in like the stratosphere, and unfortunately, Rigetti would be like pennies, right? And so, but of course, like how many dollars of funding are they away from catching up to Google, and getting that value TBD, right? But right now, I think Google and IBM have the best quantum computers. I would say Q-era is like has some really, really impressive stuff, like this Harvard startup, Harvard spin out in Boston here. There's Pascal, a French startup that's pretty hot. They're pursuing similar technology. But there's some that say superconducting is most scalable, but it has all sorts of other challenges. Honestly, I don't understand the hype right now. Like this, first of all, this is old news. This was on archive a couple months ago. I guess not everybody's a quantum nerd, so it is what it is. But to me, this was like, this is what they aimed for years ago, and they got it, which is cool. But is it going to change anything for the next 5 to 10 years apart from short-term market fluctuations? No, right? Well, 10 years maybe, but 5 probably not. So look, I am supportive of quantum computing as a technology. I think it's an important technology for our civilization. I personally decided, and a lot of my team came from quantum computing from these big tech labs, and we all left because we lost patience, right? And we started a different paradigm, right? And one that doesn't have to do error correction and leverages noise, right? Because noise was a bane of our existence, and so it's a pretty big problem. Look, I'm kind of rooting for them. It's kind of bittersweet. It's like I'm rooting for them. I want them to succeed, but at the same time, like this hype got out of control, and I'm trying to not do damage control, but temper people's expectations because there's clearly overblown. And like crypto people are using it. There's this meme of like, I'm from the NSA and I have a 1,000,000 qubit quantum computer, copy pasta. That was hilarious. That was well crafted.
10-second coherence time.
Yeah, sure. No, I think realistically, the government would just buy it from Google or IBM and, probably IBM first because they have the relationships maybe a bit closer. But, obviously, like NSA being a customer has always been the plan for quantum computing companies because for now, it's still the one algorithm that you could prove mathematically that has really big economic or strategic impact that you could point to and say, okay, we're gonna hit that. The thing that sucks for my research, having done some of the early algorithms on quantum machine learning and quantum deep learning more specifically, is that deep learning is very empirical, and similarly to like Hinton in the early days, like you can do all sorts of theory of like, hey, in principle, I could train these things with gradient descent. Here's my learning rule, blah, blah, blah. But, at the end of the day, you kind of just got to have a big enough computer to try ideas, right? And filter them. Otherwise,
just to push back on that, I mean, I'm on both AWS's Bracket and IBM's quantum platform, and it's not quite like EC2, but you can spin instances up and try things. Where does the bottleneck, do you think, or what's your hesitance there?
Yeah, you could try things with like 50, 100 qubits, but like the coherence times are not long enough for you. Like basically the noise starts dominating your computation. So you're not getting any signal. So, what I did instead was I went to X and worked on a red team with TPUs. It's on YouTube somewhere, I don't know, or it leaked in the press, whatever. But like on TPUs, we were simulating quantum computers up to like 40 something qubits using an exascale computer, right? And then we could test the algorithms. But then it's like, okay, cool. I tested an algorithm that if you had a quantum computer and scaled it, it'd be really impactful for quantum chemistry or, doing molecular dynamics, whatever. And it's like, okay, cool. But like, what do we do? I would just burn all this money to get a bit of IP that we put on a shelf and we wait, right? So it's kind of like not very cathartic. So, I don't know, like if you want to look at a public company in quantum software, friends of mine, Zapata, they went to zero a couple months ago, right? And they're all really smart guys, but they were trying to survive as a quantum software, as a user of the platform, and they died. Many such cases for quantum software startups. You basically can't survive unless you're a big tech player or you're kind of a nation state backed play. It's similar to like nuclear fusion, right? Like it's just you're promising future technology, but your current day technology beyond PR doesn't really have any applications, right? So I think that the interesting thing I will say for IonQ is that they can be used as a quantum sensor. And that's very interesting because you can sense magnetic fields, electric fields, well, in their case, electric fields specifically, but also gravity. And to me, that was some of the most exciting stuff, is that quantum sensors can sense fluctuations of gravity. For example, like is there a school bus 30 meters away from you, or maybe some not school bus, you could feel that.
Problems too, right?
What do you mean?
Well, if you're trying to run computation, these.
Oh yeah, well that's the thing, right? They're very sensitive, and you're like, how can I use that, right? So I worked on quantum sensing. That was pretty cool. But yeah, to me, like Air Force applications and precision navigation and timing, of these neutral atoms, and these ion traps are, you know, that's a killer app in the near term. I don't know how big the market is, right? It's like you can have GPS basically without a signal. You can have basically the world's best accelerometer in principle, but it's like, what are you going to do with that, right? I mean, it's good for defense, obviously, but like you can't put it in your phone. It's a big, like, it's a big, you know, like school bus sized computer, or even if it's like, you know, sedan sized, it's still not practical. You could put on payload on a big plane, maybe, or on a rocket. Then again, it's going to be tough, but yeah, I mean, it's important technology for the Earth. You know, I think quantum computing will really take off. Like, we're kind of in like this weird Cambrian era where there's a bunch of different types of quantum computers, and then over time they're going to speciate and specialize. You know, like already the photonic quantum computers are going to be used for quantum internet and interconnect. The ion traps, I think, are going to be sensors, neutral atoms, maybe graphometers. And then I would say the superconductors, TBD, TBD.
Right.
They're cool demos. But when we have silicon quantum computers, which there's a couple of companies exploring this. There's Dirac with a Q. There's 𝐤 which is helium, electrons and helium on silicon. And then there's a bunch of quantum dot companies and so on. When you have mass scale manufacturing in silicon that you can do millions and millions of degrees of freedom on a single chip, right? And they have similar fidelity, then things get interesting, but then we're just starting to play ball, right?
Yeah. And
yeah.
other than MD and quantum chemistry, encryption, I sort of don't view encryption too seriously, because by the time we get there, the data that we want to decrypt will move to PQC, and NIST is already promulgating PQC standards. So I don't know that the Chinese or NSA is going to be that excited about, you know, decrypting data from 2019 or 2018 or whenever, and in 2070, I'm not sure that 2060, I'm not sure that's really that exciting. And you know, molecular dynamics as a practitioner in the space, I personally can't see that much exciting, at least on the protein side. Maybe on the quantum chemistry side, you can get some more interesting answers. But in the pharmaceutical world, it's not that exciting to be able to simulate a many-body system for, say, 100x longer than you could with a classical computer. I don't think you learn that much more. So to me, I don't know where the app is here. And I think that's sort of the big difference between NVIDIA, which is a general purpose computer, and this, which is sort of like, you know, a handful of algorithms that actually might be supreme, you know, here relative to the classical era.
Totally. Great point. Yeah, I mean, if you look at molecular dynamics, like you need 1,000,000x speed up to make it really interesting. You know, I could circle back on that, but you know, mostly small molecule quantum chemistry is when quantum mechanics kind of dominates, like the determining the behavior. You can get like effective potentials with neural networks and DFT with a lot of compute, and then use those neural networks as proxy to do MD nowadays. But you're still bottlenecked by sort of your trajectory. Even if you have the effective potential, your trajectory simulations are your bottleneck. Correct me if I'm wrong. And so quantum would only help you get more accurate, effective potentials, right? And so that's cool. You know, we'll take it if it's there, but it's not. I think what's more interesting is like exotic materials, like understanding superconductors, materials where the correlation structure is very difficult to represent with a classical representation. So like things get really funky, like superconductors or Bose-Einstein condensate and stuff like that. But that's like very esoteric. Something maybe that's less esoteric is like nuclear.
Yeah, this is stuff we might need 100 years from now, you know, to do the Kardashev stuff you're always talking about. Today, tomorrow.
Yeah, I mean, you know, quantum computers are a card scaling technology that's needed, right? Like if we want to have, you know, really small nuclear, like if we want to have molecular assemblers, that's basically quantum robotics. So you need perception, prediction, and control, you know, and that can help you do chemistry manually. So, you know, you use far less building blocks. It's more efficient, but you could theoretically, even with X-ray lasers, like do more or less alchemy, right? You can assemble different nuclei of different elements, right? Emulate, basically we're gods. We're like supernova, artificial supernova. That's cool, right? That's deep in the tech tree. We're a bit far.
Yeah, well,
But
even just new reactions would be exciting.
yeah.
There's stuff to do.
Yeah. So to me, it's like quantum AI and quantum computers like are needed to extend the ability for intelligent beings to perceive, predict, and control the world at smaller and smaller scales, right? As you go smaller in time and space, things get quantum mechanical, right? So if you want to extend our power, our intelligence to that regime, you need these technologies. Right? You need the perception, the sensors, you need the communication, and then you need the computing and intelligence. And so that's why I worked on all of those technologies. But I paid my dues, did my 10 years.
Well, what's going on in the world
Yeah.
of thermodynamic computing?
It's pretty hot right now, not gonna lie. But yeah, I mean, I announced, a few weeks back that, not only did we, we're wrapping up our superconducting experiments, and we're going to open source that for the world. Because again, we think superconductors are slightly cursed as a substrate, and we always knew this was never the intent to end up there. But we've accelerated our roadmap for silicon, and we cracked how to do the thermodynamic computing at room temperature in silicon, which is not room temperature superconductors. People get those confused. We are doing thermocompute in silicon, not superconducting. Okay, I get misquoted sometimes, but yeah, we taped out with a major fab, one of the big 3 or 4, let's say, and getting that back end of year, and we're working with some early partners for next year, and we're going to put chips on customer tables, and that's really exciting because quantum computing, it's been going on the industry. Rigetti was 2014 or whatever when they got founded. It's like been 10 years of quantum computing industry, and there's not much to show for it. Whereas we're going to move much, much, much faster. We're trying to move 10x faster. So in a year, getting to similar degree of freedom than the best quantum computers, and a year from now, from after that, ideally where quantum computers aim to be by 2035, in terms of number of degrees of freedom. And if you actually understand how quantum algorithms work and how they get embedded in the devices, and with all the overhead of quantum error correction, you realize that if you have a 1-to-1 embedding, your number of logical degrees of freedom versus physical is 1-to-1, you have a massive advantage, right? You have a massive head start. And so, it's not, in reality, it's like more like 10,000 to 1 for quantum computing. So factor that in. So really, there's going to be no competition. And to me, it was just like years of being in quantum computing and being frustrated. Like everybody would come to quantum computing. Can you do machine learning or probabilistic inference or statistical learning or optimization really fast? It's like, well, no. Well, yes, we can kind of do it, but no, it's not going to give you a massive speed up. And even if it does on paper, by the time you take into account everything, it's not worth it. And so I got frustrated, and I was like, you know what? Let me build a physics-based paradigm that's actually good at these things, right? And we're pumping the gas, and we got something to show. We got a big chips on our shoulders, from being Waterloo grads in general. It just and then going through quantum computing as kind of the young guns that thought they knew better, and I felt like we did. And we kind of left the industry on schmedium terms. We kind of got tired and but now we're gonna have our little revenge arc. It's gonna be good. So yeah.
Yeah.